Hello everyone. Here we are given that suppose n is an even integer and h is a subgroup of Zn. Then we are asked to prove that either every element of h is even or exactly half of the members of h are even. Okay. So given n is even. Alright. And for every n we know that Zn. We can consider Zn. Okay. And consider a subgroup h of Zn. So what is the thing we have to prove? Take such a subgroup of Zn. It could be any subgroup of Zn. Okay. Now look at the elements in H. We will notice that either every element of H has to be even, or suppose we are getting some odd element in H. In that case, H will satisfy the property that only exactly half of the elements in H are going to be even. Okay, so there will not be any imbalance. Okay, so suppose we are taking a subgroup H whose cardinality is, say, for example, 10. Okay, then suppose it has an odd element, then 5 of the elements in H will be even, 5 of the elements in H has to be odd. Okay, there cannot be a mix up like 6 of them are even and 4 of them are odd and things like that. It is going to be exactly half. Okay, in other words, we can also say that exactly half of the members of H are odd. Okay. Okay, so let's try to prove this. So what are we saying? Either every member of H is even, in otherwise exactly only half of them can be even. Okay, so let H be any subgroup. Okay, we are taking arbitrary subgroup. Okay, let H be any subgroup of Zn. Okay, now we don't know how H looks like or what are the properties of H, but just suppose that all elements of H are even. Okay, when we are inspecting, suppose that all elements of H are even, then we are done, right? Then the proposition is proved. In this particular case, nothing is there. Okay, in that case, we are done. Okay, so suppose not. Okay, okay, if all the elements of H are even, then we are done. Okay, now suppose that is not the case. That means there exists at least one element H. Okay, in H, such that H is odd. Okay, there exists at least one element which is odd. Okay, if this is the case, we are done. Now we are considering the other case. Suppose at least one of the element is odd. In that case, we have to prove exactly half of the members of H. Exactly half of the members of H are going to be uh, even. Okay, all right. So what will we do? We will do one thing. Let's consider all the elements in H that are even. Call that set as HE. What is HE? It is the set of all elements of H that are even. Okay. Similarly, consider HO. It is a set of all elements of H that are odd. Okay. Now, what we will do is we will show cardinality of HE is equal to cardinality of HO. Okay, that means number of elements in HE is same as number of elements in HO. That means number of elements that are even is equal to number of elements of H that are odd. Okay, so that exactly half of members of H are going to be even in that case. Okay, so let's try to prove this. Now here we have two sets, right? To prove that their cardinality is the same, what should we do? We should show that there exists a bijection between them, right? To show there exists a bijection between HE and HO. Okay, if we show that there exists a bijection between them, then of course we are done, right? Then the cardinality had to be same and we are done. But just before proving the existence of a bijection, let's just inspect HE and HO. Can they be odd? Sorry, can they be empty? Okay, so just check. We know that 0 is an element of the group, and since H is a subgroup, 0 is an element of H, right? Because H is a subgroup. And 0, it is even, so definitely 0 is an element of HE. Okay, so HE is never empty. Okay, HE can never be empty. Now, which case are we considering? We are not considering the first case. In the first case, every element of H were even. So in that case, if we are considering HO, it would have been empty. But here we are considering the case that there exists an element H in H such that H is odd. So at least H is there in capital H. Okay. So sorry, HO. So this implies that HO cannot be empty. Okay. So we have two non-empty sets, and suppose we are giving a bijection between them, then their cardinality has to be same, right? Okay. So let's try to construct a bijection. So now for constructing a bijection, we are going to use very simple idea that if we are adding an even element, if we are adding an even number and an odd number, we are getting an odd number. That's basic idea of what we are going to do. Okay. So let x be in HE, that means x is going to be even. Okay. Consider x plus h. Okay. X plus h, it is going to be odd, definitely, right? Because h is even, x is even, h is odd, so x plus h has to be odd. Okay. Moreover, we know that x is an element in HE. HE is contained inside capital H, so x is an element of capital H, and small h is also in capital H. Now, H is a subgroup, so it has to be closed under this addition. So x plus h is also an element in H. Okay, so we have an odd element which is there in H. Okay, so x plus h must be in HO, right? It has to be an element in H, and it is odd, so it is in HO. Okay, so this gives us a idea about how to construct this bijection. So the what I will do is consider a map phi from HE to HO such that, take an element x here, I will map it to x plus h. Okay, note that here h has been fixed. Okay, we are beginning with we are observing the subgroup H, and then we came up with an odd element H. We are freezing that H. Okay, now this H is fixed always. Now consider phi from HE to HO. X is getting mapped to x plus h. Okay, if phi is a bijection, we are done. Okay, so we will try to show that phi is a bijection. Okay, for phi to be bijection, phi has to be 1 1 and onto. So is phi 1 1? When will be when will a function f be 1 1? Take x and y. Suppose f of x is equal to f of y, then x has to be equal to y. In that case, f will be 1 1, right? So to show that phi is 1 1, begin with phi of x, x1 and x2. Okay, so suppose phi of x1 is equal to phi of x2. Okay, then what will it mean? It will mean that, what is phi of x1? It is x1 plus h. Okay, phi of x1, it is going to be x1 plus h. And what is phi of x2? It is going to be x2 plus h. Okay, now x1 plus h is in capital H, x2 plus h is also in capital H, small h is there in capital H. So all of these are elements in a subgroup, and we can use the cancellation property in the groups, and we can cancel h, and then we will get that x1 has to be equal to x2. So phi of x1 is equal to phi of x2 implies that x1 is equal to x2. So phi is 1 1. All right. Now is phi onto? To show that phi is onto, take an element from the codomain. Here it is going to be HO, and we have to show that it has a preimage. Okay, so let y be in HO. All right, we have to show that phi that we can find an element such that phi of that element is equal to y. Okay, now what is the possible candidate? Okay, let's think about it. So here we have y is odd. We also know that h is in ho, it is also odd. Okay, so h is in ho. Now consider minus h. Okay, minus h, this h is in capital H, so capital H is a subgroup. Okay, so inverse of h, which is minus h, will also be there in capital H. Okay, since capital H is subgroup, inverse of h, which is, in this case it is additive group, so we are considering minus h. Inverse of h, which is equal to minus h, will also be there in capital H. Now since h is odd, minus h is also odd, so we'll have minus h is also in ho. Alright, now consider this y plus minus h, which is same as y minus h. Okay, so it is an odd element minus another odd element, so it has to be even, right? So this is even, and we know that y minus h, this we are taking y in capital H, minus h in capital H, so y minus h, it is definitely going to be there in capital H. Okay, because h is a subgroup, and y minus h is even, right? So together we will have that y minus h is in he, right? It is in he. So consider phi of y minus h. What is this going to be? This is going to be y minus h plus h, which is going to be y. Okay, so take any element in the codomain, it has a pre-image. So phi is onto. So phi is both 1 1 and phi is 1 1 and phi is onto. That means phi is a bijection. Since phi is a bijection, cardinality of HE and cardinality of HO has to be equal. So that means exactly half of the elements in H are even and other half is odd.